Okay, in this chapter we go back to integration. However, we're going to need all the derivative rules, just no partials like we just got done with, but we will need to go back to derivative. Alright, so to start this out, there are a few different techniques for integration. We are going to use the substitution technique in this first video. And the reason this is needed is we're going backwards from derivatives. Sometimes it's, I can't look at these examples and tell you what the original function is that I took the derivative to get this, necessarily. Sometimes you can, most often no. And remember, integration doesn't have, I had two blue lines here, integration does not have like a product rule like derivative has. Derivatives by far, even though they could get ugly, are much easier because we have the product rule, quotient rule, chain rule, and no matter what function I throw at you, as ugly as it might be, you can do derivative. Integrals up to this point, we've been very limited. Okay, so here's how it works. We create this new variable u, and typically it's going to be the ugly part. Okay, and what we're looking for is, can we see its derivative somewhere? So I had underlined this preemptively, but if I make u this x squared plus 4, I can see its derivative, which I'm going to call du, right here. Right? That's the whole goal, what we're looking for. Do you see some function in there and its derivative? Now, I do this off to the side because it can get ugly, just like product rule and quotient rule can. Okay, so we make u x squared plus 4. And then what we are doing is the derivative of this with respect to x. Typically, I don't write what I have here in red. Okay, so in the next examples, when I don't write that, you'll see why. But to show why exactly we're getting what we're getting, I went ahead and wrote it. All right, so the derivative with respect to x of u is du dx because the variables don't match. Okay, that was, we learned that in Calc 1 as well. Now the derivative of the right-hand side is just 2x because the derivative of 4 is 0. So the step that I'm not writing is this. We move this dx over, even though it's not really du divided by dx, it works algebraically. Okay, and we discussed this in Calc 1. So this step here, along with the d dx, I typically don't write. Okay, I just have u equals x squared plus 4. du is 2x dx. This dx is very important because when we're making this substitution, right, this original problem has a dx right here. So when I change everything to u's here, it's important to get rid of all of the x's. Now the way I do this, you can YouTube it and probably find other methods as well. Some people solve for dx instead, and then they make that replacement. Okay, I'll leave that up to you. This is the way I do it. This is the way that I prefer it. So now let's go in and make these substitutions. We had said u is x squared plus 4. So I now have u to the 5th. Okay, that takes care of all of this here. Then du is 2x dx, so that takes care of all of the rest, right? That becomes du. This integral now is simplified or simple back to the basics. The power rule for integration is just add one to the exponent and divide, right? So we get u to the 6 over 6. Because it's not a definite integral, we have plus c. I'm very bad about forgetting the plus c, so I apologize ahead of time if I make that mistake. Now one last step. Our original problem had nothing about u's in it, so it'd be very weird to say the integral of that is u to the 6, right? So we go back in and resubstitute, right, back substitute. This u was x squared plus 4, but now it's to the 6th power plus c. And the divide 6, you can leave it divide 6 or write it as 1/6. Either way, right, they mean the same thing. So now we integrated this more complex integrand by substitution, introducing this variable u and proceeding. Okay, let's look at one a bit more complex. Like I said, u is typically the ugly part. Often we don't include the exponent. Notice I didn't put to the fifth here, right? I just took the inner part. So let's use that same strategy for the next one. I'll let u be the inside of the parenthesis 1 plus ln x. Its derivative of 1 is 0, derivative of ln x is 1 over x. Remember that the derivative of ln, I'm going to say d over dx ln x is 1 over x. But if we have anything other than x, then what we say is du over u for simplicity, the derivative of whatever this is, right, whatever the x is, over itself. So one other thing, sometimes I'll forget that as well, we have the dx, don't forget the dx. Okay, now let's substitute. 1 plus ln x we called u, so we now have u to the third, and then 1 over x dx would take care of everything else because this divide x, right? I could say that's 1 over x, and then I have dx. So all of that is du. Again, now it's a simple integral, u the fourth over 4 plus c. And last, we back substitute. What is u? U is 1 plus ln x to the fourth. I'm going to go ahead and write it as 1/4 plus c. Okay, these take some practice, finding out what the u is, but once you get it, it's pretty straightforward. Once you find the correct u, and like I said, sometimes you do have options. Sometimes you choose a different u and it could work. Okay, this last example now, we're finding the function. Okay, we're given the slope. Okay, this is the slope, which means that's the derivative, right? Slope and derivative are synonymous. So if that's a derivative and I want the original function, remember if we integrate the derivative, so the integral of this derivative here, the slope, will give me the function. Kind of. We'll have a plus c. We'll fine-tune that here in a minute. Okay. All right. Well, we don't have parentheses here, but we do have this square root, right? So kind of a good rule of thumb, make u the ugly part, whatever's in parentheses, or in this case, the square root. So let's give that a try. I'll switch colors here. U equals x squared plus 9. Du then is 2x dx. All right. Well, it looks pretty good, except for the fact I don't have a 2x, right? I don't have a 2x, I only have an x. Easy fix though, if you're off by just a constant, a multiplier, if I can multiply this by 2, then I could also divide by 2 or multiply by 1/2. But I didn't change the original function, right? Because 1/2 of 2 is 1, and I'm right back to where I started. I didn't change what I have. All right, now let's make this substitution. So du, I have all 2x dx, that's du, right? Over this u, this is u, but it's square root of u, so u to the 1/2, only because we're doing integrals and it's easier to think of radicals as a exponent, right? Rational exponent. I still have this 1/2 out front. I didn't get rid of that, right? I had to put the 2 in there to have du, but I still have this 1/2 out front. All right, now using our integration techniques, this actually is u to the negative 1/2. Right, and now we add 1 and divide, so that becomes 1/2 u to the positive 1/2 divided by 1/2, or multiplied by 2, plus c. Our 2's end up going away. That's not always the case. That's all right. So u to the 1/2, but u is x squared plus 9, right? Let's back substitute. And as 1/2 power, it's easier to think of as square root. And what we were getting is our original function. But a function, we can't just have a c. We don't just have a constant in there. And that's where this information here comes into play. Okay, and that's really just x and y, right? Or f of x. So last we make the substitution to find c. So y is 8, x is 4. So we have the square root 4 squared plus 9 plus c. So that's 16 and 9 is 25. Subtract 5 on both sides, we get that c is 3. Now we're done. We just plug 3 in for c, and we have our function. Square root of x squared plus 9 plus 3. Okay, so that's the function who has this slope that passes through that point.